Okay, good morning, afternoon, good evening, wherever you happen to be. This morning I'm going to go through the cells, modules, and arrays solutions for NRGY 243 solar PV. And I'm just waiting on Sri Lanka Grace Center to get online, but while I'm doing so, I'm going to dive into the solutions. So let's take a look here. First question is the open circuit voltage of a PV cell is, and let's take a look at the answers. First, I'm going to just hop out and define what the open circuit voltage is for you. So there's two critical things to keep in mind. That's the open circuit voltage and the short circuit current. And we can go out here, let's just see. And the things you want to type in are VOC and ISS. Or no, it's SSI, short circuit current. Okay, that did not bring up the right one. Always fun here. And just going to bring up PV cells, images. Yeah, here's the curve I wanted. All right, so typically the voltage is on the horizontal axis, and the current is on the right axis, on the vertical axis. Sorry, I'm trying to do two things at once here. Okay, looks like I've got the pad going now. Let me just restart it. Okay, here we go. There we go. So here's voltage, and here's current. Another thing you always need to keep in mind, cells, panels, and arrays. Another thing you always need to keep in mind in any power system is that power equals an across variable times a through variable. So in the case of a solar array, you can think of it this way, just a plus, a minus, the voltage is the across. You're always measuring voltage across two terminals, and then the current is the through. The I equals through. All right, now, the way to think about this is if we take a multimeter and measure the voltage with the open circuit. So we're actually going to break the circuit here, measure it. So we'll put a multimeter on it. Multimeter from here to here. With our multimeter. The voltage, this stands for open circuit. It means there's no load on it. There's no load. We don't have no lights are on, no TV's going, no fridge. So the open circuit, we break it, measure it. That's the VOC, or voltage open circuit. Okay, and that's the most voltage that you'll ever get out of the panel. But you have to remember that power equals voltage times current, and right here you have equals VOC times 0 equals 0. Oh, it looks like my Hangout group is there. Okay, let's see. Chat.
Hello?
Hello. I can hear you, but I don't see your video. Just pause it here for a moment.
No, last time you cleared all the questions, you know?
Okay, good, good.
Clear.
Okay. Well, so what I thought I would do this morning is I think our next lesson is the cells, modules, and arrays. So I thought I would just start on that. Okay, so I'm going to share my screen, and I'll go through the cells, modules, and arrays quiz, and I will show you I'll show you the notepad, and I'll show you the quiz. So hopefully you can see everything. Let me start sharing my screen now. Note 1. Share. Okay, so now I think you can see the screen with my notepad.
Yeah.
Okay, good. So what I'm covering is the first problem on the quiz. It says the open circuit voltage is what? And we want to know what the voltage is, and we want to know how that might behave with temperature. So let's take a look here. So what I'm showing is a single panel, and each panel has a cell. So these are cells, cells, cells. Each one is a little cell. And there might be 32, there might be 40, maybe up to 60 cells on a single panel. So the whole thing is a panel. And it will have several cells. And what I'm showing here is the open circuit voltage. So VOC. And what that means is we've taken a multimeter, which is a little box, and I don't know if you have these yet, but you're going to become very familiar with them. The multimeter will measure between the plus and the minus, so everything here is the minus. And if you break that open, you're going to measure the voltage. And what I was showing here is that anytime you're measuring power, so power is going to be measured in watts equals volts times amps. Anytime you're measuring power, you're going to have an across variable, and you're going to have a through variable. So across and through. This is very important. Very important for any engineering technology, for any technology. Okay, so in this case, the voltage is the across variable. So I've tried to write that right here. The voltage is the across variable, and the current, or the amperage, is the through variable. So first we can measure the across variable, which is voltage, VOC, and power, of course, equals volts times amps. So in this case, when we have the open circuit, so open circuit, C-I-R-C-U, open circuit, no electrons flow. So no electron flow. But there's still voltage. It's pushing. Well, how much? Voltage open circuit. So power equals voltage times current. VOC times 0. Why is it 0? Well, because this is the current, and down here, right down here, current equals 0. Just as over here, voltage equals 0. So at the open circuit voltage, power equals voltage times current, VOC times 0 equals 0. Okay, so the next thing to do is to measure the short circuit. So this is ISS, short circuit voltage, and there, in this case, we've touched both lines together. So electrons flow. So this is where we have electron flow, no load. No load. No lights, no electricity is being drawn. It's just flowing through the current, through the panel, through every cell in a big circle like this. Yeah. Good. Okay, so in this,
Could you explain from the beginning?
okay, yes, I can. So I'm going to try to share the whole screen. Give me a second here. I'm going to share just the word. So what we're covering is just this very first problem. Okay, can you see the Microsoft Word question now? So you should see on your screen cells, modules, and arrays. And it says choose all correct answers. Do you see the question now? Do you see the question? Okay. Unfortunately, I can't hear your response. I think I might try to share the full screen. Can you see the Microsoft Word question? I don't think so. Hey, good morning. Let me do the full
Yeah, he
screen.
is a English master.
Oh, okay. Hi, good morning.
Next morning. Yeah, it's evening.
Yeah. Well, it's nighttime there, I think, right?
Yeah, it's nice and warm here.
Oh, good. Oh, good.
I could carry on.
Yeah. Okay.
Excuse me.
Yes. Okay. Okay, so I think what I'll do, I'm going to just finish this lecture, and then you can come back and watch it again.
Okay.
Okay, it's and this is also, this portion is, it's very important. It's very fundamental to how photovoltaic panels work, because we're going to go over all the different components as well as the fundamentals of how current and voltage flow through them. So I'm going to go back to the I'm going to go back to the question. So here's the question in Microsoft Word. It says choose all the correct answers. Open circuit voltage in a PV cell is either half a volt, 12 volts, varies with the cell surface area, or decreases with increasing temperature. So as it turns out, A and D are both correct. And what I want to do is show you some fundamentals of the cells first so we can get to this answer, and then we'll get to this answer. So again, we're looking at the open circuit voltage. So what I've begun showing here with this graph, so this entire box here is the panel. That's the panel, the solar panel. And again, the panel is, I'll just pull up a picture really quick so you know exactly what I'm talking about. So we can see, let's just pick this one here. We can see this entire square is the panel, this rectangle is the panel, but if we count the cells, there are 1, 2, 3, 4, 5, 6, times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 6 times 12, 72 cells.
We can see the question summary.
Okay? So 72 cells. Okay, good. This is getting recorded. Okay, so now what I've shown is that the power in any technology is the across variable times the through variable, and the across variable is volts, and the through variable is amps. So when we multiply volts times amps, of course we get power in watts.
Uncle,
Yes?
could you share what you do now? We can see your question summary.
Oh, what can you can't see the other portions? Okay, let me.
Yeah. Then what you
Okay. Yeah, I'm trying to share the entire screen. Chrome wants to share the contents of your screen. Choose what you like to share, your entire screen. Well, I'll just have to show this first. So you can see the solar panel now, right?
Yeah.
I'm making a big circle around the solar panel. Okay, so in the solar panel, there are 1, 2, 3, 4, 5, 6 cells in this direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 6 times 12, 72 cells in this panel. 72 cells in this panel. Now we'll go back and I'll show you how to get to the open circuit voltage. And I'll share the notepad. So now you can see my notes, I hope, where it says cells, panels, arrays. You see that? You see that now, my notepad?
Yeah.
Okay, good. Okay. So what I've drawn over here is a panel. It's a little rectangle on the right side. And I've just sort of drawn in the cells, just sort of as a sketch. So the entire technology is the panel, and there are 72 cells in the panel. So what we're looking for is this thing called the open circuit voltage. Open circuit voltage. I'm drawing a circle around it here, because what we've done is we've plotted volts on this axis. There's volts on the horizontal axis, and we've plotted amps on the vertical axis. So the two important things to know about the cell for now are the open circuit voltage, And what I've shown up here is that if you have a multimeter, so I've drawn MM for multimeter. Multimeter will measure volts, it will measure current. You will have those in your hands very shortly. And the voltage is the across variable. So if we have no load, well, I should say no load and no circuit. So no electrons are flowing. So they're all blocked, no electron flow. We're going to measure the open circuit voltage. So at this particular case, since there's no current, I equals 0. The power also equals 0. So open circuit voltage times 0 equals 0. But typically, for one cell, VOC equals about 0.5 volts. So that's the first part of the answer. That's the first part of the answer. And that's just a fundamental principle of most silicon cells. Some are a little higher, some are a little lower, 0.5 cells. But we also know that as the temperature rises, so as temperature goes up, VOC goes down. So this is as temperature increases, voltage decreases. Okay, so as temperature increases, voltage decreases. That's very important. So that's what I've shown here in this cell, in this exit full screen. Let me try to share. Share screen. Your entire screen. Okay, I'm going to go back and try to share the entire screen. Okay, so can you see the Microsoft Word now?
Yeah.
So, okay, good. So we've answered this part, that the open circuit voltage is about 0.5 volts. And the next part to know is that the open circuit voltage decreases with increasing temperature. So the answer is A and D. The other thing I want to remind you of, if we go back to our panel, if we are at the short circuit, so this is the short circuit. So what does short circuit mean? Short circuit means that the electrons flow, the electrons are flowing through the technology, they flow, but there's no load, no resistance. Everything just goes around and around in a circle like this. Woo! So there's no lights attached, no other motors attached, it's just going around and around. So in this case, the power equals the voltage, which is now 0, times the short circuit, whatever that might happen to be, equals 0. So at this point, power is 0. At this point down here, power is 0. So, of course, the best place to have power would be out here. Best power. Because the power is going to be the area of this triangle. So let me draw a new, let me get a new pen going here. So this red line All of this, this is the power. So power equals volts times amps. And this is going to be the best right here, where you have relatively high voltage, relatively high current. So if you go too far to the left here or too far down, you end up with zero power. So right at this point, and this is called the maximum power point. Maximum power point. And typically what you see in a cell is a computer chip, a little circuit that makes sure that this happens. Okay, so the next question is, what happens when temperature goes up? And I think the next question actually says that. Okay. All right. So this next question says, assuming low wind speeds, the operating cell temperature of a PV at peak sun could be near 77 degrees, could be near what temperature at 77 degrees Fahrenheit or 25 degrees Celsius. So in this case, what happens is, if there's relatively little wind and a lot of sun, the temperature can actually get quite hot. And I'll draw that. So I've already told you that as the temperature goes up, the voltage goes down. Another thing that happens in the cell so I'm just going to draw one little cell here. And we know the voltage is approximately 0.5 volts, and that's DC. The cell is also a resistor. So we can think of the cell as being a resistor. So here's the volts, here's the current. The current comes through. I'll just say this is VI and this is V out. And so what happens when you have, let's just draw, here's the sun, and the temperature equals 25 degrees C. As the electrons flow through, they make resistance. And as the temperature goes up, the resistance also goes up. So R is the resistance, T is temperature. R is the resistance. And the unfortunate thing that happens is that as the resistance goes up, the temperature also goes up. So it ends up being this vicious cycle. So as this temperature of the air goes up, the temperature of the cell goes up as well. And what we've said here is 122 degrees Fahrenheit. Let's just go and check and see what that is in centigrade. So 122 F to C. It can be as high as 50 degrees centigrade. So equals 50 degrees Celsius. And of course we know that as the temperature goes up, the voltage goes down, and that makes the power go down. So one thing we might consider doing is blowing some air. So if we have a fan, and we've done this before, if we have a fan that blows air, or if we had some water, we could also take some water and flow it through to make it cooler. So the air would make it cooler. We could also have water. And so now as the temperature goes down, the voltage goes up and the power goes up. That's a good thing. Okay, so this is also very important to think about. And let me just show you one of the panels that we're hoping we can get to Sri Lanka. These are relatively new. We're going to use them in Browning soon. This is something that I'm working with a colleague. Cool solar, here we go. And I have shared this with Dr. Naresh too. Okay, so what we can see here is that we have the solar panel on the top, but on the back we have solar thermal. And the nice thing about that is some of the energy comes from electricity, some of the energy can go into heat, and now what we can see is that we get energy from both. So here's the energy, the blue is the energy from the solar along the bottom, and this nice red is the energy from the heat. The nice thing about taking the heat away from the solar is it makes the blue go up, and it makes the solar panel last that much longer. So hopefully we can get some of those to you for your upcoming practicum. Okay, let's move along. Sorry?
I'll be the solar from heat or sunlight.
Can you type your question? Oh, shoot. Oh, come on. Oh.
How do we take energy to solar panel from heat or sunlight?
Oh, okay, I understand your question. So I think your question is how do you get heat from both? How do you get solar? Okay, so that's a good question. So in the case of, okay, so I'll go back here. So this panel will have, it'll have electricity is here. We can just think of electricity as being here. So here's your voltage. This is kind of funny to write with this pen. Here's your voltage. Here's the plus. Here's the minus. But there's also, so this is the electricity at the top, but there's also down at the bottom, this is water. So water. This is funny. Water is in this bottom. So water comes through the bottom. So electricity is on the top. you can see each one of these is a little, so this is a cell. Here's another cell. Here's another cell. But through here, this is the water. H2O. And it goes in here,
Yeah.
and it comes out here. Pretty cool, huh? Yeah, okay, good. Very good. So the electricity is on the top and the heat is on the bottom. Okay, so the next question is, a blank is a thin flat disk of material. So in this case, it's just called the wafer, and we can go and look at this. Actually, I love showing this picture. These are my other students. Each one of these little cells that you can see, they soldered together. So many dozen of these, they built each one of these by hand. And so they were soldering wafers. Solar PV wafer. So what we did when we built our cells, each one is made from a little wafer. And the wafer that's being shown here is polycrystalline. So all of the colors, there's a lot of different crystals in the silicon right there. So that's just called a wafer. Wafer. Okay, so the next question, it says blank is the process of adding small amounts of impurities to alter the electrical properties. And the answer is doping. Now, here's the important part to know about this. So I would like to take you out to the dynamic periodic table. This is one of my favorites. I suggest that you visit this site frequently. Okay, so this is the periodic table of the elements, and what we can see here, this is silicon right here. Element number 14 is silicon. Okay, and when a solar cell is made, what happens is that you put in either boron or phosphorus. So typically silicon is the main element, but you put in either boron, which is number 5, or phosphorus, which is number 15. And that's called doping. Now if we go, what you should look at, here's silicon, it has these orbitals. It's also important to know that silicon sits right below carbon on the periodic table. So if we look at carbon, it has these 2 electrons here in the 2p orbital. One up and another up. So it's missing 1, 2, 3, 4. It's missing 4 electrons. It's the same with silicon. Is missing 1, 2, 3, 4 electrons in the 3 silicon. So you can see it has 1, 2, 3, 4 neighbors. 1, 2, oops. Oh, come on. 2, 3, 4. And that's how it binds with those 4 electrons. So you can think of one silicon in the middle, and then 4 neighbors. 1, 2, 3, 4. But here's what happens, and I'll show you what we do in NRG 102. I don't think we covered this fully. If we go out, and this is in chapter 3. This is in chapter 3. Hopefully my laptop will behave here. It seems like it's getting a little bit slow. I think I'm really pushing my machine to the limit here. Okay, so these are the early days of solar. Okay, so what this picture is showing, let me see if I can make this a little bit larger. What we're looking at, each one of these little circles is a silicon atom. So at the top, part A, what we can see, each of this is silicon. So silicon, silicon, silicon. Each one of these dots is an electron. And each one of these arrows is an electron moving around in the lattice. So the electrons can move. So what we're looking at is an atomic lattice of silicon. This is the fundamental component of the solar cell. But if we put in a phosphorus, these greens are the phosphorus. The greens are the phosphorus. There's an extra electron. See the extra electron with nowhere to go? That's because the phosphorus has one extra electron right here. See that third electron in the 3p? That's what that electron is. Okay, and now we can go down here to boron, and you can see there's a missing electron right there. There's an opening, and that's called a hole. H-O-L-E, a hole. So if we take this whole thing, let's take the whole thing, copy, paste, tools, highlighter, eraser. If we replace this with phosphorus, now we have an extra electron, and it'll move. It'll move around. And so the extra electron is what allows electricity to flow. We can also take this, tools, highlighter, eraser, medium. If we instead take out a silicon and put in a boron, then there's an electron missing. There's nothing there. And that'll allow an electron from somewhere else to come in to fill it. Okay, so here are the 3 different lattices. Now this is what it looks like in the cell. So we're looking right down at the fundamental level of the wafer, of the cell. So there are 3 things that can happen, or 4 things that can happen when the photon comes in. So this is sunlight. This is the photon coming in. And when it comes in, this electron-hole pair. So what I just said before, the electron-hole pair is formed. The photon will make that happen. It'll break apart the lattice and make that happen. So in this case, you actually get a little bit of current. Or in the case of 2, here comes another photon, and if it hits up in this N region, you're not going to get current until the electron flows down and flows all the way through the circuit. So here's your ammeter measuring current. This is a conductor on the back that's collecting the electrons. And here's your collector or your conductor sitting on the top. So the N region, that's the negative region. So this is going to be the N region. N is negative. N is negative because electrons are negative. That's the little negative right there. Electrons are negative. If we go back again, we can have, here's the P region. The P region is boron. So this is a hole. So a hole is positive. So boron, so B equals boron. And this is where it's a little bit confusing because P equals phosphorus. So unfortunately, P means phosphorus, but P also means positive, and the positive is because there's a hole. And I know that's very confusing, but it's just the way it is. Okay, so back to the question. That was a lot, I know, but we were basically covering doping. And doping means whether you put in boron or phosphorus. So all solar panels are made, most of them are made from silicon, and you put in either boron to create holes, and here's the hole. See, there's that missing electron right there. And so the extra electrons want to flow towards the holes. Or if you dope with phosphorus, it makes an extra electron that wants to flow towards the holes. There's some nice pictures here I can show you. You can think of it like cars. So if a photon comes in and hits this car, it then moves up. So if energy comes in, it can move it up, and now it can flow. Now it can flow. I wish I had a better cartoon going, but that's the basics behind it. Okay, let's move on. Okay, doping. Based on the temperature effects on silicon PV output, choose 2 variables that are preferable. Okay, so the temperature again is key. So if you want to have a roof mount array, what's the best thing to do? So if you have 6-inch standoff mounts, 6-inch standoff mounts allows the cooling. So remember, we showed this before. And we could have, if the roof is down here, this would be 6 inches. So we can draw that. Let's show a picture of this. I'll see if I can find a nice picture. So here's a good picture. Here's a good picture. So you can see right here, this allows for the panels to stay cool. The panels can stay cool because there's air flowing behind them, just like I drew in this picture. So if you have air or water, it keeps the panels from getting too hot. Okay. And again, if the shingles are light colored, they also stay cool. So if it's white, they stay cool. If it's black, it gets hot. Okay, number 6. PV module warranties, 20 years or more. They can last a long time. I think it says this here maybe on our sheet. Let's see. Well, it doesn't say that, but yeah, these guys should put the warranty on their literature. 20-year warranty. They will last a long time. Especially if you want to send your PV into space, right? So if we show this, it's very difficult to go up and fix these panels, right? So these solar panels on the International Space Station, you want them to last a long time. 20 years or more. Yeah. Okay. Number 7, blank is the ratio of maximum power to the product of the open circuit voltage and short circuit current. Oh, this is a good question. So this is the fill factor. Oh, that's a very good question. So what this is showing, if we go back here, let me see if I can go back here to this one, tools, pen. Yeah, so if we could get every bit of electricity, we would go all the way from here to here. So this guy, I'm just going to draw this portion out here. So if somehow we could get P max would equal VOC times ICC, but we can't. We can't. So because we need some kind of space. We need some kind of space on the panel for the electronics. Oh, and the best place to show that, I think, is here. So let's zoom in. Woo, it's a little too much. So there's always some space around each cell, around each wafer, that no electricity goes in. So the fill factor, FF equals V times I, whatever the voltage is here, divided by VOC ISS. Oh, I wrote CC. ISS, short circuit. ISS, short circuit. Okay, so the fill factor equals the voltage times the current at the maximum power point divided by VOC, which is down here, times ISS, which is up here. So that's the fill factor. And it might be 85–90%, depending on your panels. Okay. So maybe let's just say 85 to 90%. Okay, number 8. Choose all the correct answers. Choose all the correct answers. the short circuit current of a PV cell. So, well, it can be safely measured. It's not going to be much current. It's just going to be a few amps. It can be very safely measured. So this is wrong. That one's wrong. Increases with increasing surface area. That is correct. The bigger the panel, the more current you have. So this is ISS. I short circuit. So this is ISS we're looking at here. So the next one is increases with surface area. Yes, the more panel you have. So as the area goes up, does current. So this is green. That's good. Okay. Increases significantly with increasing irradiance. Yeah, it does. As sunlight, so does current. So that's good. And then the next one, increases significantly with temperature. No. Panel performance decreases with increasing temperature. Okay. All right, the next one. The temperature rise coefficient is the coefficient for estimating the rise in temperature above ambient temperature due to insolation. So that's the answer there. So insolation. And insolation is just how much sunlight hits the panel. Solar irradiance is how much energy is coming out of the sun. That's a subtle difference there, but important to know. Okay, number 10. A blank curve is the graphic representation of all possible voltages. That's the IV curve. The IV curve. And we've been doing this all day long. So this whole thing is the IV curve. IV curve, good. And I, of course, is current. V, of course, is voltage. IV curve. Okay, the next one. Silicon is commonly doped with what to make a cell? Fortunately, we've already covered that. That's phosphorus and boron. Phosphorus and boron. So if we go back here, here's phosphorus, number 15. And the reason is it's got that extra electron, or boron, number 5, with the missing electron. Okay, next question. Number 12. A blank is a unit of electromagnetic radiation. Oh, this is a good one. That's a good one. And the answer is the photon. The photon. So a proton, we know that sits in the nucleus. The electron, we know that sits around the atom. And the neutron also sits in the nucleus. So these are all in the nucleus orbiting the atom, the nucleus, atomic nucleus, and this is in the nucleus. And this is, of course, light from the sun. That's your photon. Okay. Standard test conditions. Standard test conditions rates module performance at an irradiance of what? So this is also very important, and we've done this a couple times before. It's 1,000 watts per square meter. At the top of the atmosphere, sometimes you'll see 1,500, but this is the typical, and I think there's a nice image of that too. Yeah, so here you might see greater than 1,000, but this is typical. This is like in the morning, in the evening, you've got more air mass, so this would be your 1,000. In Sri Lanka, you might see 1,500. I've seen 1,500 in Missoula. It happens. It can happen, kind of rarely. So this green is the theoretical output from the sun, and the sun would be at 6,000 degrees Kelvin. Air mass 0. This is typically what our sun looks like right at the very top of the atmosphere when there's almost nothing blocking the sunlight. And this air mass 1.5, this curve is all of the radiation that comes through the atmosphere and hits the modules and hits the arrays. And all of these missing portions are different absorptions. So different molecules in the atmosphere will absorb sunlight. But the AM 1.5 corresponds to this condition, and this is 1,000 watts. And maybe I'll draw a little quick picture on that. So if we do this, if the sun is right overhead, so right here would be air mass 0. So AM is air mass. AM is air mass. This would be air mass 1. But if we come through this way, this is air mass 1.5, and this is going to be about 1,000 watts per square meter. This guy up here would be closer to 1,360 watts per square meter. And it's the fact that all this air, this is the Earth, of course, all of this air is absorbing energy. How is it absorbing it? Well, it's absorbing it through greenhouse gases. The greenhouse gases also absorb some of the heat. Okay. Next one, blank is a PV device consisting of a number of cells connected. This is a module or panel. Let's say or panel. I've been calling it a panel all day. That's fine. An array, this is a set of modules. An array is a set of modules. And I'll show you what an array is. This is what you'll be building. So this is an array, a big solar array. Next one. Which of the following terms refer to silicon-based PV materials? Well, cadmium tellurium, amorphous, monocrystalline, gallium arsenide, polycrystalline, and CIGS, or ribbon. All of those are terms. And we don't need to get into that very much right now, but typically what you'll be seeing, this is a typical cell, and polycrystalline. This is more expensive. We'll just say more expensive, higher performance. And the polycrystalline is also typical, less expensive, lower performance. And a ribbon, this is just multiple cells in series. Cadmium, tellurium, these are sometimes used in making cells, and gallium arsenide, those are also sometimes used. So here's galcium, here's arsenic, here's tellurium, and there's gallium. So those are also used. Cadmium is over here, number 48. Okay, 16. Bypass diodes. Bypass diodes, they allow current to go around shaded cells. So this is very important. So in an array, so I'm just going to draw a very simple array. With 6 cells. Six cells. So they're wired this way, and let's just say each one has 0.5, 0.5, 0.5, 0.5, 0.5, 0.5. So the voltage for the panel equals 6 times 0.5 volts equals 3 volts. So this would be a very small panel. And if we wired it this way, I'll just draw it simply. In, out, in, out, in, out. So again, this is a very simplified way, but here's your positive, here's your minus. You'd have 3 volts. But let's just say you have a tree nearby. So here's a tree. And over here is the sun. I'm going to put the sun down here. And if we have, if the sunlight is coming through, it'll hit all of these guys, but there could be a chance that if we had another, the sun is trying to get here, it can't get through, and it will not get to this down here. So what ends up happening is this is in the shade. This is shaded. And so what happens, this becomes broken, and the voltage equals 0, right? Frowny face. But if you have a bypass diodes, if you have diodes inside, and it's a little too complicated to draw, but let's just say we had, we'll put some diodes in here, some diodes in here, some diodes in here, diode, diode, diode. So D equals bypass diode. Even though there's shade, current can still flow. It can still go this way. Smiley face. Smiley face. Okay, so that's the point of that question, is if you have the bypass diode in the panel, you can still have sunlight even though this guy is in the shade or broken. Okay, so that's very important for making sure that you get the most out of your panel. Okay, 17. It is safe to measure short circuit current on which of the following? Battery. No, never short circuit battery. No, do not short circuit a battery. The battery will be damaged. PV panel, okay. That's basically going to give you the ISS that we talked about before. Wall receptacle, no. Very dangerous. You probably know that already. Generator, no. Never. Good way to blow the generator. So yes, PV panel is okay. PV panel is okay. And all that means on the short circuit is that you're touching the wires together. Okay. 18. The blank is the point on the IV curve where the product is maximum. And we showed this already. Let me just review. This is the maximum. IMPP, maximum power. Maximum power point. MPP. Maximum power point. And that's also where this area, this nice big red cell is the largest. Very important. All right. I think we're doing very well today. This is a fun lesson. Thank you. Okay, the last question. Blank is the condition of a device operating at negative voltage. Well, the answer is called reversed bias. So in that case, rather than the cell making current, it would be collecting current. It would be, or rather than it making voltage, it would be collecting voltage. So this is a bad condition. Bad condition means that a cell might be dead. Okay, well, that was a lot. I think we've gone for 1 hour and 15 minutes, and I hope this lesson comes through well. It's a very fundamental one. It's so nice to see you all today. Thank you very much for staying with me. That was a lot. That was a lot. And I'll record the video. I'll make sure it stays up, because what we just did right now, that'll help you when you start doing your hands-on, when you start touching the multimeters, testing the panels, and I know we're working on sending those. So very soon, all of this boring classroom stuff will be over, and you'll get to use your hands with the technology. So thanks again. Hope you have a good night.
Thank you and goodbye.
Okay, thank you so much. Bye-bye. Bye.